that 0.5% number is greater than or less than 5%. So obviously it's less than, it's like basically 10 times less than 5%. But that's a great question. Yeah. So the link here was you calculate this probability in question one, and then you compare it to 5% in probability. Okay.
What if you change around the hypothesis instead of saying that they're unrelated but they are related?
Yeah, so that becomes more difficult. So you could, in theory, test that hypothesis, but it would require you to specify exactly how related they are, if that makes sense. So basically, it's like if you thought there was a perfect deterministic relationship, like you were like, my model of the world is that Steve Jobs is going to wait around until the next iPhone comes out, and then he's going to die the day after, then you could test that hypothesis. Now, you would in fact fail. So even with that like pretty crazy deterministic model of the world, you would fail to reject that model, given the actual data, because he in fact, he actually died that day, and so then that would sort of, you'd be like, well, I can't confirm my model. But you could certainly imagine that maybe he had died like 4 days afterwards, and then if that happened, you'd say, okay, well then I reject the model that I just posited, because under that model where it's like a deterministic relationship, there was like a 100% chance that he died the next day and a 0% chance he died any other day. So since he died like 4 days later, you'd say, well, there's a 0% chance of that happening, so I'm going to reject my model. More realistically, you'd probably do something like, I think that they're pretty strongly related, but it's not purely deterministic. So maybe it's like, my model is that he will die within 10 days of after the iPhone is released, or maybe you'd be like, I think he's going to die within a week, but like plus or minus 5 days or something like that, based on sort of your belief on sort of how much randomness there is, and then you could again sort of maybe test that model using the data. But so basically you have to specify exactly how strong you think the relationship is, right? Because the problem comes when you say, I think there's some non-zero relationship, but it can be arbitrarily weak, and if it's like an arbitrarily weak relationship, then it's almost impossible to distinguish that from just zero relationship unless you have like an infinitely large data set. The other thing that I should say is that when I wrote up here, do you reject or accept the hypothesis that the two events are unrelated? That's actually like not kosher. So if I wanted to be a little bit anal about it, what I would write is, do you reject or say fail to reject the hypothesis that the two events are unrelated? It turns out that like you can reject the hypothesis, but you can never truly accept it, and it's basically for exactly that reason that I just said. That so if you had observed him dying like 5 weeks after the iPhone, then you would have said, well, the fact that he died 5 weeks after the iPhone doesn't seem that like strong relationship. It doesn't seem like that strong a coincidence, basically. And so that fact is certainly consistent with those two events being unrelated, but it also would be consistent with there being some like very weak relationship between them. That somehow like releasing the iPhone like weakened him very slightly or something like that. And so you couldn't actually, if you would observe that outcome, you couldn't say, well, I accept this hypothesis, like basically I accept this model that we built up before. You could just say like, well, I can't reject that model, but obviously I can't reject some other models that are very similar to it. Okay, so that's like, I mean, this is this is not like in terms of like the practice of economics and social science in general, and science, like you're not going to see that many scenarios exactly like this, but the thought process there and the logic behind it is basically identical to the logic behind a normal statistical significance test with these t ratios that are distributed normally, no pun intended. Okay, so then I think, let's see, the last thing that I want to do today to just finish this part out is to apply the knowledge of regression to a table of results from an actual research paper. So this is one of the papers that's in the course. Let me also say that, so now we're getting to the portion of the course where there are actual research papers on the syllabus, and there's some readings, and like if you look at the syllabus now, we're basically entering into the section 2 part. And so they're going to, the next few lectures, we'll be discussing some of these readings from the course, so you might want to take a look at them. But this is from one of the papers in the course, and the regression model. So these are coefficient estimates from a regression, and the regression model that is being estimated here is basically something like the following. So the dependent variable is housing values. So, and I think that it's actually probably the log of house price. So yi is equal to the natural log of the price of property I, where I is indexing all of these housing transactions. So what you have here is you have a data set of housing transactions in Nevada, and what the author is interested in doing is basically trying to figure out how health risk affects these housing values. So in particular, he has some measure of leukemia risk based on the location of where houses are, and he wants to see how that relates to the price that the house actually sells for. So yi is equal to the log of house prices, and then like x1i is leukemia risk, x2i is equal to lot size, x3i is equal to basically floor space, so it's like the square footage of the house, and you have some other things, so like x4i is age, and a couple other variables as you go down there. And so the regression model here is yi is equal to beta naught plus beta 1 x1i, which is leukemia risk, plus beta 2 x2i, which is the lot size, plus beta 3 x3i, which is the floor space. Yeah, it does. Okay, so I'll put the squares into. So it's beta 3 times x2i squared plus beta 4 times x3i plus and beta 5 times x4i, like 6 times x4i squared. There might be a few more variables in there from the table, and then plus some residual term ei. So I guess so just in the last 5 minutes then, in the groups again, why don't you answer these, it'll be 3 questions. So one question is going to be, what's the ceteris paribus effect of leukemia risk on house values, assuming that assuming that there's no selection bias or omitted variables bias. The second one will be which of the coefficients in the first column are significant? And then the last question is just come up with one potential omitted variable. So remember, again, the data here, he has observations on all of these housing transactions when a house is sold on the market. He observes its sale price, and he knows like basically what its lot size was, what its floor space was, building age, and then he also has this measure of leukemia risk by sort of different neighborhoods or different geographies. And so he's also folding that into the regression here as a variable. So just like concentrate on the first column, you can ignore the next two columns. But in like 4 minutes, I guess, answer those questions, and then I'll have you guys give your answers and be done. So. Yeah, so it is a diff and diff study, but actually don't worry about that for the moment. Just interpret the regression here. So the regression is housing values on these, let's see, 1, 2, 3, 4, I think 6 variables that he's identified. And just in case there's, just be clear, the things aren't in parentheses, it's a coefficient, and then the things in parentheses are standard errors that correspond to that coefficient. Huh? Yep. Yeah. Why do we have what?
You have x 2 times and 1 times squared.
Oh, because if you look in the table, it says lot size, which next to it is lot size squared, which is x2 squared. And be clear that, remember again, the housing value is in log, so you can just tell me its effect on the log housing value if you want. Okay. Does a group besides group 6 want to volunteer their answer? Huh? You can keep going until you go wrong, which won't necessarily happen. Okay. So for number 1, what is your interpretation of that effect, or what do you think the effect is?
So status parameters, equity, all the other variables.
Right.
If leukemia risk, say, increase by 1, then the housing prices decrease by 12 degrees.
Yeah, so that's correct. So the so what you know, which I haven't mentioned yet, is that if the right hand or the left hand side variable, the dependent variable, this y variable, is in logs, then the coefficient on one of the x variables can be interpreted as basically the percentage change in the left hand side variable for 1 unit change in the right hand side variable. And we don't have time right now, but in a later class I'll just write up the short math behind that. But so when you look there at that coefficient, then you'd say like, oh, minus 0.123. I know that is that basically implies that if I increase leukemia risk by 1 unit, then approximately speaking, housing value should drop by about 12%. So question 2, is that statistically significant?
Like this variable?
Yeah, sure, just for that variable.
Yeah, it is.
Okay, yep. Because the t-stat is greater than 2. Actually, are all the variables in that particular column statistically significant? Yep. Yeah. So I think, unless I missed something, I think if you go through all of those t statistics are greater than 2, and that's partially a function of the fact he has over 10,000 observations, so it's a pretty large data set, and these variables are pretty strongly related to each other. I mean, you imagine that like floor space is related to housing prices. Then the last, okay, well, we don't have time for the last question, but we can talk about omitted variables on Friday.